Hi guys, today we're going to do the 2.1 notes for calculus. It's about the tangent and velocity problems. It's really a very small preview to the world of calculus. And before I start, I want to list some concepts and words that we're going to come across in these notes that you need to know. One is secant line. Another is tangent line. Another is, this is not going to be new to you, average rate of change. Another is going to be instantaneous rate of change. Another is going to be average velocity. And the other one is going to be just velocity, or in our book, sometimes they use the word instantaneous velocity, but you can just say velocity. And then delta y over delta x, change in y over change in x. Okay, so I'm going to draw something here for you. Let's suppose I have a curve, any f of x function, it doesn't matter. There, we'll call that f of x. And I have a line, I have a dot right there, and I have a dot right there. If I connect those two dots, that line is called the secant line. So a secant is a line that connects any 2 points on a graph. So a secant line has to connect 2 points. Here's another secant line. That's a secant line. Okay. I want you to imagine, for example, let's go back to the secant line. I want you to imagine this dot. So this dot stays stationary, stays fixed, but that this one starts moving closer and closer and closer and closer to this dot. So if it goes here, then the secant will look like that. If it goes here, the secant will look like that, until it gets so close to that dot that there's only one dot. And so let me redraw that same sketch. What we're going to have is just the one dot and then a line that looks like that. That line is called a tangent line. A tangent line touches literally one point on the curve. 1 point. PT means point. Now this is not a tangent. Not a tangent. Because a tangent has to stay completely above or below the curve. Okay? But this is a tangent. Tangent. This is a tangent line. Okay? This is a tangent line. So tangent line. Tan for tangent. Tan for tangent. Okay? Okay, so secant line, tangent line. Let's talk about the average rate of change. Let me redraw that sketch again. Actually, I'll draw another sketch. So let's draw a parabola. Okay, regular old y equals x squared parabola. And suppose I take the point 1, 1, and some other point, it doesn't matter. If I connect those points, I have what? I have a secant line, right? S-E-C for secant. Is it, so let's say this is the point 2, 4. Let's just pretend. Is it possible to get the slope of this red secant line? It sure is, because slope, to find a slope, how many points do you need? You need 2 points, right? You would do y2 minus y1 over x2 minus x1, and you could get the slope. The question is, if you have a tangent line, let me draw a tangent line here, right? Touches the curve, tangent line, tangent. Can you find its slope? Well, no, because how many points do you need to find a slope? You need 2. And in a tangent, it only hits the curve in 1 point. Okay, so back to the secant line. If I find the slope of this line using 2 points, what's another fancy schmancy name for slope? It is average rate of change, right? The slope, so let me write that, super important. Slope of secant line, which uses 2 points on the curve, is called the average rate of change. So what do you call the slope of the tangent line? Well, a wild guess, I'm sure you're guessing right now, which uses only 1 point. So you can't really calculate a slope using 1 point. You can't do a y2 minus y1 over x2 minus x1. Here we're doing y2 minus y1 over x2 minus x1, right? Remember that slope formula? But we don't have a y2 minus y1 over x2 minus x1 when there's only 1 point. So I'll show you how to get that, but you can't use this formula. But we call that slope of the tangent line, the slope of any tangent line is called the instantaneous rate of change. Super important words here, okay, that we need to know. Okay, so let me do an example to put it all together, and then I'll get to the other words on our list in just a moment. By the way, delta y over delta x, that's your y2 minus y1 over x2 minus x1. Change in y over change in x. So you know that that is the slope formula that we've done since, I don't know, 5-6 years ago when they first got introduced to it. All right, let me go on and do a problem. Okay, so suppose y equals x squared sorry, not suppose. Graph y equals x squared, not suppose. Sorry. Okay. Find the equation of the tangent line at the point 1, 1. Okay, in calculus, if you want to be a successful calculus student, you have to be able to connect your work to a graph. You have to be able to visualize graphs. So I'm going to graph a simple y equals x squared parabola. Here we go. Everyone knows what a simple parabola is. And I'm going to do some points. That's 0, 0. This is 1, 1, right? 1, 1. And I'm going to visualize with you, find the equation of the tangent line. The tangent line at 1, 1. So it would look like this. This is what it would look like. This is the tangent line. I am asking you for the equation. This is a line, a straight line. What does the equation of a line look like? It looks like y equals mx plus b. We are going to find this. Okay, the exact one. All right, well, what do you need for the equation of a line? Of course you need a slope and a point. Guess what? You've got the point. It's 1, 1. So that's done. Now you need a slope. This is the one that's missing. So you can't just guess. You have to actually mathematically calculate it. Well, if we don't have 2 points to find a slope, we're going to have to do our best. All right? So what I'm going to do is I'm going to show you a few secant lines. So let's go to the point 2, 4. And if we draw a secant line, this is what it would look like through the 2 green dots. But that's really not very accurate. That doesn't even resemble my tangent line. So what if I scoot the point closer in to here? Then I connect this dot and this dot. Well, that secant line is more like this tangent line, but it's still not good. What if I scoot that dot even closer, and I mean microscopically close, and then I connect those two dots? That secant line is looking very much like the tangent line. So the concept in this section is, can I calculate the slope of a secant line using 2 points that are so close to each other that the tangent line and the secant line won't even be that far from each other? So then I'll be able to predict the slope of the tangent line. So I'm going to ask you to do a few problems. Calculate the slope of the secant line from, ready, x equals 1 to x equals 2. That was the 1, 1 and the 2, 4. Then from x equals 1 to x equals 1.5. Notice I'm keeping the first point stationary, but I'm scooting that second x value closer to the 1. So this is not going to be a great prediction here. This one will be a little bit better. This one will be so much better. Look how close those two x values are. So the dots would be much closer to each other. Let's see, x equals 1 to x equals 1.01. And then finally, x equals 1 to x equals 1.001. And we're going to see a trend when we do our calculations. So we're going to be calculating a slope. All right, so for the slope, of course, it's going to be y2 minus y1 over x2 minus x1, right? So all of these, look, it'll be x2 minus x1 on the bottom. 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 And so what we have to do is generate the y2 minus y1 value. So how do you do that? Well, you plug in x into the function. What do you get when you plug in 2 into the function? You get 4. Minus, when you plug in a 1 into the function, you get a 1. What happens? So this is going to be y2 minus y1. That means, so this would be x1, x2, x1, x2, x1, x2, x1, x2, x1, x2. All right, so if I plug in x2 into the function, what's 1.5 squared? It is 2.25 minus 1 squared is still 1. What's 1.1 squared? It is 1.21 minus 1 squared is 1. What's 1.01 squared? It is 1.0201 minus 1. What's 1.001 squared? It's 1.002001 minus 1 squared is 1. Don't be too impressed. I did these problems before the notes, and I did not just do those in my head. Okay, so then when you punch all those into the calculator, you get for this one, 3. For the second one, you get 2.5. For the third one, you get 2.1. Then you get 2.01, and finally 2.001. Okay, what is the trend? What is the prediction? As the second x value gets closer and closer to the first value, what do you think is happening to the slope of that secant line? It is a secant line because I'm using 2 points. It looks like they're approaching the number 2. So we can conclusion. The slope of the tangent line at 1, 1 is 2. M is slope. Y equals mx plus b. So the equation of the line, equation of tangent line Okay, I'm going to use the y minus y1 equals m times x minus x1 formula for the equation of line. This is called the point slope form. So I'm going to plug in my point and 2 for the slope. This is my 1 comma 1. And if I want to put it in y equals mx plus b slope intercept form, it'll become y equals 2x, what is that, negative 2 plus 1 minus 1. This is the equation of the red tangent line, y equals 2x minus 1. That red line that goes to the point 1, 1. All right, let's see. What's next? Okay, so now I have to finish up the notes with 2 more examples, but they won't be too long. And I have to tie all of this into velocity. All right, so this is number 3. How does this tie into velocity? Okay, so recall that rate times time equals distance, right? So rate is now the same thing as velocity. Okay, velocity is a speed, so that's a rate, like 25 miles per hour, 15 miles per hour. Velocity is speed with direction. So if I say negative 25 miles per hour, it doesn't mean I'm going slower than 25 miles per hour. It just means I'm going in the opposite direction, like north and south. So I'm going to replace r with v, because v is a rate. Time is time, and then I'm going to replace d, distance, with h for height. Same concept. These are both physical distances. And so if you solve for v, you'll notice that it's h over t. Velocity is height over t. The change in height over the change in time. Okay? It is also a slope. So velocity is, this is super duper important, okay? Velocity is going to be the instantaneous rate of change for any position function. By the word position, I mean height or distance, okay? Average velocity is the same as average rate of change for any position function. Okay, so by the way, remember I can insert the word instantaneous velocity, but it's kind of redundant. Velocity already means instantaneous. All right, so in our example, this is how it's going to go. Okay, so the example is if, example, EX means example. If a rock is thrown upward on the planet Mars, its height, there it is, this is the position function, is, its height in meters, I should say, so those are the units of measure. Its height in meters is h of t equals 10t minus 1.86 t squared, and t, where t is in seconds. So, meters and seconds. All right. A, find the average velocity over a few time intervals, over these time intervals. Okay, so 1. The first time interval is 1 to 2. This is not a point. Look at the brackets. This is like T1 and T2, from time 1 to time 2. Well, if I'm finding average velocity, we know that average velocity is the same thing as average rate of change. And what's a less fancy word for average rate of change? It's regular old slope. Slope formula. So if average velocity, here it is, velocity equals change in height over change in time, then my calculations are going to be h of 2 minus h of 1 over 2 minus 1. That's h with the second h minus the first h, plugging these two into the function, over 2 minus 1. The second time interval I want is from 1 to 1.5, not 15, 1.5. So it would be h of 1.5 minus h of 1 over 1.5 minus 1. The third one I want is over the time interval 1 to 1.1. So h of 1.1 minus h of 1 over 1.1 minus 1. The fourth one is going to be 1 comma 1.01. And I want, so these will be given and you will have to calculate these. H of 1.01 minus H of 1 over 1.01 minus 1. And then the fifth one will be time interval 1 to 1.001, H of 1.001 minus H of 1 over 1.001 minus 1. So notice these, again, those time intervals are becoming smaller and smaller and smaller because what are we trying to predict? After we do a few average velocities, we're probably going to use the answers to predict the instantaneous velocity. Okay, we're going to see a trend. So I already punched these in for you. So I did h of 2. That means I took a 2 and I plugged it into here and here. And then I took a 1 and I plugged it into here and here. I subtracted them over, 2 minus 1. And I got 4.42. Then I got 5.35, 6.094, 6.26, and 6.3. So what's the trend? It looks like they are approaching about 6.3-ish. They're rounding out to about 6.3. All of these are average velocities because how many points did we use to calculate a slope? 2 points, an x1 and an x2, a y2 and a y1, x2, x1. What are the units of measure? It's height over time. So it is meters per second. They're all meters per second, okay? All right, and then the second question I'm going to ask you about this problem is, use your computations to predict the instantaneous velocity at time equals 1 exactly. Not from time equals 1 to time equals whatever, just at that single solitary time. So we say it could be about 6.3 meters per second at that very point. All right, and then I'm going to wrap up the notes with just a super quick example, which I have right here. Okay, so this is the last thing, and it's water is leaking out of a tank. The table, which I'm about to show you, shows volume, which we're going to call V of t, capital V, not lowercase v for velocity, but capital V for volume, of water remaining in the tank in gallons, there it is, unit of measure, after t minutes. Okay, so time is in minutes. All right, and here's the table. So quickly draw this. I'm not going to do too many. So this is time in minutes, and this is velocity in gallons. Okay, so 5, 10, 15, 20, 25, 30. And then we've got 694, 444, 250, 111, 28, and 0. All right, here's the one question I'm going to ask you. It says, estimate the slope of the tangent line at t equals 10. I'm only giving you one time. That means it has to be a tangent line, not a secant line, because it's only one time value, by averaging the slopes of two secant lines. Okay, interesting. You guys, if I don't have a function to plug into, like they never said, oh, velocity equals 10t minus 1.86, whatever. I don't have a function. I just have a whole bunch of table of values. The only way I'm going to get an approximate slope of tangent line is if I take two secant lines, get their slopes, and average them. But you have to know which. There's a whole bunch of secant lines we could do. We could take this point and this point. You know, this could be x1, x2, y1, y2. Get a slope using these two. That's one point. Here's a second point. We could do it with these 2 points and then average those two answers. But that's silly because I want it around time equals 10. So what I'm going to do is I'm going to choose a point involving time equals 10. So I'm going to choose these 2 points. Okay. I'm going to calculate a slope. M means slope. And then I'm going to choose these 2 points and calculate a slope, and then average those two to get an approximate for this one. So the first slope that I'm going to calculate uses the points, use 5,694 and 10,444. And for the second slope, I'm going to use the points 10,444 and 15,250. So here I go for the first one. It's going to be 444 minus 694 over 10 minus 5. And the second one is going to be 250 minus 444 over 15 minus 10. And did I do these calculations already? Let me see so that I can show you the answers. It looks like, give me a minute. I'm looking at my other notes that I did for you. 15 and 10. Okay, so this one gives us negative 38.8. And did I do this one? Let me see. I did not do this one. Let's just do it. What's 694 over 444? No, wait a minute. I think I did do it. Oh, Well, anyway, I can't find it. That's okay. So it'll be what? 250 is the difference. What is this? Negative. Oh, can I do the math? Yes, negative 250 over 5, which is negative 50. Okay, right? 200 is, yes. Okay, so I get negative 50 for this slope, negative 38.8. And so the answer to my problem is when I average the two answers. So negative 50 plus negative 38.8 over 2, whatever that is. I don't even know. What is that? Negative 88.8 over 2, and that is negative 44.4. Okay. I hope my math is right. You guys can correct me, but you know the basic concept. Get two slopes using these 2 points, then these 2 points, and then average them. And so this would be the answer. Of course, we need units. It's gonna be what were the units? Gallons per minute. And that's the end of our notes.